CPU caches. The first bus that used a cache had only one level of cache. Unlike later level 1 caches, it was not split into L1D for data and L1I for instructions. Almost all current CPUs with caches have a split L1 cache. They also have L2 caches and, for larger processors, L3 caches as well. The L2 cache is usually not split and acts as a common repository for the already split L1 cache. Every core of a multi-core processor has a dedicated L2 cache and is usually not shared between the cores. The L3 cache and high-level caches are shared between the cores and are not split. An L4 cache is currently uncommon, and is generally on dynamic random access memory, DRAM, rather than on static random access memory, SRAM, on a separate die chip. That was also the case historically with L1, while bigger chips have allowed integration of it and generally all cache levels, with the possible exception of the last level. Each extra level of cache tends to be bigger and be optimized differently. Other types of caches exist that are not counted towards the cache size of the most important cache as mentioned above, such as the translation look-aside buffer, TLB, that is part of the Memory Management Unit, MMU, that most CPUs have. Caches are generally sized in powers of 2, 8, 16 etc. KB or MIB, for larger non-L1 sizes. Although IBM Z13 has a 96 KB L1 instruction cache. 66 clock rate. Most CPUs are synchronous circuits, which means they employ a clock signal to pace their sequential operations. The clock signal is produced by an external oscillator circuit that generates a consistent number of pulses each second in the form of a periodic square wave. The frequency of the clock pulses determines the rate at which a CPU executes instructions and, consequently, the faster the clock, the more instructions CPU will execute each second. To ensure proper operation of the CPU, the clock period is longer than the maximum time needed for all signals to propagate, move, through the CPU. In setting the clock period to a value well above the worst-case propagation delay, it is possible to design the entire CPU and the way it moves data around the edges of the rising and falling clock signal. This has the advantage of simplifying the CPU significantly both from a design perspective and a component count perspective. However, it also carries the disadvantage that the entire CPU must wait on its slowest elements, even though some portions of it are much faster. This limitation has largely been compensated for by various methods of increasing CPU parallelism, see below. However, architectural improvements alone do not solve all of the drawbacks of globally synchronous CPUs. For example, a clock signal is subject to the delays of any other electrical signal. Higher clock rates and increasingly complex CPUs make it more difficult to keep the clock signal in phase, synchronized, throughout the entire unit. This has led many modern CPUs to require multiple identical clock signals to be provided to avoid delaying a single signal significantly enough to cause the CPU to malfunction. Another major issue, as clock rates increase dramatically, is the amount of heat that is dissipated by the CPU. The constantly changing clock causes many components to switch regardless of whether they are being used at that time. In general, a component that is switching uses more energy than an element in a static state. Therefore, as clock rate increases, so does energy consumption, causing the CPU to require more heat dissipation in the form of CPU cooling solutions. One method of dealing with the switching of unneeded components is called clock gating, which involves turning off the clock signal to unneeded components, effectively disabling them. However, this is often regarded as difficult to implement and therefore does not see common usage outside of very low power designs. One notable recent CPU design that uses extensive clock gating is the IBM power-based Canon used in the Xbox 360. That way, power requirements of the Xbox 360 are greatly reduced. 67. Clockless CPUs. Another method of addressing some of the problems with a global clock signal is the removal of the clock signal altogether. While removing the global clock signal makes the design process considerably more complex in many ways, asynchronous, or clockless designs carry marked advantages in power consumption and heat dissipation in comparison with similar synchronous designs. While somewhat uncommon, entire asynchronous CPUs have been built without using a global clock signal. Two notable examples of this are the ARM-compliant Amulet and the MIPS R3000 compatible Mini-MIPS. 68. Rather than totally removing the clock signal, some CPU designs allow certain portions of the device to be synchronous, such as using asynchronous ALUs in conjunction with superscalar pipelining to achieve some arithmetic performance gains. While it is not altogether clear whether totally asynchronous designs can perform at a comparable or better level than their synchronous counterparts, it is evident that they do at least excel in simpler math operations. This, combined with their excellent power consumption and heat dissipation properties, makes them very suitable for embedded computers. 69. Voltage regulator module. Many modern CPUs have a die-integrated power managing module which regulates on-demand voltage supply to the CPU circuitry, allowing it to keep balance between performance and power consumption. Integer range. Every CPU represents numerical values in a specific way. For example, some early digital computers represented numbers as familiar decimal, base 10, numeral system values, and others have employed more unusual representations such as ternary, base 3. Nearly all modern CPUs represent numbers in binary form, with each digit being represented by some two-valued physical quantity such as a high or low voltage. F, a 6-bit word containing the binary encoded representation of decimal value 40. Most modern CPUs employ word sizes that are a power of 2. For example 8, 16, 32 or 64 bits. Related to numeric representation is the size and precision of integer numbers that a CPU can represent. In the case of a binary CPU, this is measured by the number of bits, significant digits of a binary encoded integer, that the CPU can process in one operation, which is commonly called word size, bit width, data path width, integer precision, or integer size. A CPU's integer size determines the range of integer values it can directly operate on. G. For example, an 8-bit CPU can directly manipulate integers represented by 8 bits, which have a range of 256, 28. Discrete integer values. Integer range can also affect the number of memory locations the CPU can directly address. An address is an integer value representing a specific memory location. For example, if a binary CPU uses 32 bits to represent a memory address, then it can directly address 232 memory locations. To circumvent this limitation and for various other reasons, some CPUs use mechanisms, such as bank switching, that allow additional memory to be addressed. CPUs with larger word sizes require more circuitry and consequently are physically larger, cost more and consume more power, and therefore generate more heat. As a result, smaller 4 or 8-bit microcontrollers are commonly used in modern applications, even though CPUs with much larger word sizes, such as 16, 32, 64, even 1 to 8-bit, are available. When higher performance is required, however, the benefits of a larger word size, larger data ranges and address spaces, may outweigh the disadvantages. A CPU can have internal data paths shorter than the word size to reduce size and cost. For example, even though the IBM System/360 instruction set was a 32-bit instruction set, the System/360 Model 30 and Model 40 had 8-bit data paths in the arithmetic logical unit, so that a 32-bit had required 4 cycles, one for each 8 bits of the operands. And, even though the Motorola 68000 series instruction set was a 32-bit instruction set, the Motorola 68000 and Motorola 68010 had 16-bit data paths in the arithmetic logical unit, so that a 32-bit had required 2 cycles. To gain some of the advantages afforded by both lower and higher bit lengths, many instruction sets have different bit widths for integer and floating point data, allowing CPUs implementing that instruction set to have different bit widths for different portions of the device. For example, the IBM System/360 instructions A was primarily 32-bit, but supported 64-bit floating point values to facilitate greater accuracy and range in floating point numbers. 30. The System/360 Model 65 had an 8-bit adder for decimal and fixed point binary arithmetic and a 60-bit adder for floating point arithmetic. 70. Many later CPU designs use similar mixed bit width, especially when the processor is meant for general-purpose usage where a reasonable balance of integer and floating point capability is required. Parallelism. The description of the basic operation of a CPU offered in the previous section describes the simplest form that a CPU can take. This type of CPU, usually referred to as subscalar, operates on and executes one instruction on one or two pieces of data at a time. That is less than one instruction per clock cycle, IPC and LT1. Model of a subscalar CPU, in which it takes 15 clock cycles to complete 3 instructions. This process gives rise to an inherent inefficiency in subscalar CPUs. Since only one instruction is executed at a time, the entire CPU must wait for that instruction to complete before proceeding to the next instruction. As a result, the subscalar CPU gets hung up on instructions which take more than one clock cycle to complete execution. Even adding a second execution unit, see below, does not improve performance much. Rather than one pathway being hung up, now 2 pathways are hung up and the number of unused transistors is increased. This design, wherein CPU's execution resources can operate on only one instruction at a time, can only possibly reach scalar performance, 1 instruction per clock cycle, IPC equals 1. However, the performance is nearly always subscalar, less than 1 instruction per clock cycle, IPC and LT1. Attempts to achieve scalar and better performance have resulted in a variety of design methodologies that cause the CPU to behave less linearly and more in parallel. When referring to parallelism in CPUs, terms are generally used to classify these design techniques. Instruction-level parallelism, ILP, which seeks to increase the rate at which instructions are executed within a CPU, that is, to increase the use of on-die execution resources. Task-level parallelism, TLP, which purpose is to increase the number of threads or processes that a CPU can execute simultaneously. Each methodology differs both in the ways in which they are implemented, as well as the relative effectiveness they afford in increasing the CPU's performance for an application. H. Instruction-level parallelism. Basic 5-stage pipeline. In the best-case scenario, this pipeline can sustain a completion rate of 1 instruction per clock cycle. One of the simplest methods for increased parallelism is to begin the first steps of instruction fetching and decoding before the prior instruction finishes executing. This is a technique known as instruction pipelining, and is used in almost all modern general-purpose CPUs. Pipelining allows multiple instructions to be executed at a time by breaking the execution pathway into discrete stages. This separation can be compared to an assembly line, in which an instruction is made more complete at each stage until it exits the execution pipeline and is retired. Pipelining does, however, introduce the possibility for a situation where the result of the previous operation is needed to complete the next operation, a condition often termed data dependency conflict. Therefore, pipelined processors must check for these sorts of conditions and delay a portion of the pipeline if necessary. A pipelined processor can become very nearly scalar, inhibited only by pipeline stalls, an instruction spending more than one clock cycle in a stage. Improvements in instruction pipelining led to further decreases in the idle time of CPU components. Designs that are said to be superscalar include a long instruction pipeline and multiple identical execution units, such as load store units, arithmetic logic units, floating point units and address generation units. 71. In a superscalar pipeline, instructions are read and passed to a dispatcher, which decides whether or not a simple superscalar pipeline. By fetching and dispatching 2 instructions at a time, a maximum of 2 instructions per clock cycle can be completed. Instructions can be executed in parallel, simultaneously. If so, they are dispatched to execution units, resulting in their simultaneous execution. In general, the number of instructions that a superscalar CPU will complete in a cycle is dependent on the number of instructions it is able to dispatch simultaneously to execution units. Most of the difficulty in the design of a superscalar CPU architecture lies in creating an effective dispatcher. The dispatcher needs to be able to quickly determine whether instructions can be executed in parallel, as well as dispatch them in such a way as to keep as many execution units busy as possible. This requires that the instruction pipeline is filled as often as possible and requires significant amounts of CPU cache. It also makes hazard-avoiding techniques like branch prediction, speculative execution, register renaming, out-of-order execution and transactional memory crucial to maintaining high levels of performance. By attempting to predict which branch, or path, a conditional instruction will take, the CPU can minimize the number of times that the entire pipeline must wait until a conditional instruction is completed. Speculative execution often provides modest performance increases by executing portions of code that may not be needed after a conditional operation completes. Out-of-order execution somewhat rearranges the order in which instructions are executed to reduce delays due to data dependencies. Also, in case of single instruction stream, multiple data stream, a case when a lot of data from the same type has to be processed, modern processors can disable parts of the pipeline so that when a single instruction is executed many times, the CPU skips the fetch and decode phases and thus greatly increases performance on certain occasions, especially in highly monotonous program engines such as video creation software and photo processing. When just a fraction of the CPU is superscalar, the part that is not suffers a performance penalty due to scheduling stalls. The Intel 5P Pentium had 2 superscalar ALUs which could accept 1 instruction per clock cycle each, but its FPU could not. Thus the 5P was integer superscalar but not floating point superscalar. Intel's successor to the 5P architecture, 6P, added superscalar abilities to its floating point features. Simple pipelining and superscalar design increase a CPU's ILP by allowing it to execute instructions at rates surpassing 1 instruction per clock cycle. Most modern CPU designs are at least somewhat superscalar, and nearly all general-purpose CPUs designed in the last decade are superscalar. In later years, some of the emphasis in designing high ILP computers has been moved out of the CPU's hardware and into its software interface, or Instruction Set Architecture, ISA. The strategy of the very long instruction word, VLI, causes some ILP to become implied directly by the software, reducing the CPU's work in boosting ILP and thereby reducing design complexity. Task-level parallelism. Another strategy of achieving performance is to execute multiple threads or processes in parallel. This area of research is known as parallel computing. 72. In Flynn's taxonomy, this strategy is known as multiply instruction stream, multiple data stream, MIMD. 73. One technology used for this purpose was multiprocessing, MP. 74. The initial flavor of this technology is known as symmetric multiprocessing, SMP, where a small number of CPUs share a coherent view of their memory system. In this scheme, each CPU has additional hardware to maintain a constantly up-to-date view of memory. By avoiding stale views of memory, the CPUs can cooperate on the same program and programs can migrate from one CPU to another. To increase the number of cooperating CPUs beyond a handful, schemes such as non-uniform memory access, NUMA, and directory-based coherence protocols were introduced in the 1990s. SMP systems are limited to a small number of CPUs while NUMA systems have been built with thousands of processors. Initially, multiprocessing was built using multiple discrete ECPs and boards to implement the interconnect between the processors. When the processors and the interconnect are all implemented on a single chip, the technology is known as chip-level multiprocessing, CMP, and the single chip as a multi-core processor. It was later recognized that finer-grain parallelism existed with a single program. A single program might have several threads, or functions, that could be executed separately or in parallel. Some of the earliest examples of this technology implemented input/output processing such as direct memory access as a separate thread from the computation thread. A more general approach to this technology was introduced in the 1970s when systems were designed to run multiple computation threads in parallel. This technology is known as multi-threading, MOUT. This approach is considered more cost-effective than multiprocessing, as only a small number of components within a CPU is replicated to support MOUT as opposed to the entire CPU in the case of MP. In MOUT, the execution units and the memory system including the caches are shared among multiple threads. The downside of MOUT is that the hardware support for multi-threading is more visible to software than that of MP and thus supervisor software like operating systems have to undergo larger changes to support MOUT. One type of MOUT that was implemented is known as temporal multi-threading where one thread is executed until it is stored waiting for data to return from external memory. In this the CPU would then quickly context switch to another thread which is ready to run. The switch often done in one CPU clock cycle, such as the Ultra SPARCT1. Another type of MOUT is simultaneous multi-threading, where instructions from multiple threads are executed in parallel within one CPU clock cycle. For several decades from the 1970s to early 2000s, the focus in designing high-performance general-purpose CPUs was largely on achieving high ILP through technologies such as pipelining, caches superscalar execution, out-of-order execution, etc. This trend culminated in large, power-hungry CPUs such as the Intel Pentium 4. By the early 2000s, CPU designers were thwarted from achieving higher performance from ILP techniques due to the growing disparity between CPU operating frequencies and main memory operating frequencies as well as escalating CPU power dissipation owing to more esoteric ILP techniques. CPU designers then borrowed ideas from commercial computing markets such as transaction processing where the aggregate performance of multiple programs, also known as throughput computing, was more important than the performance of a single thread or process. This reversal of emphasis is evidenced by the proliferation of dual and more core processor designs and notably, Intel's newer designs resembling its less superscalar 6P architecture. Late designs in several processor families exhibit CMP, including the x86-64 Optron and Athlon 64X2, the SPARC Ultra SPARC T1, IBM Power 4 and Power 5, as well as several video game console CPUs like the Xbox 360's triple-core PowerPC design, and the PlayStation 3's 7-core cell microprocessor. Data parallelism. A less common but increasingly important paradigm of processors, and indeed, computing in general, deals with data parallelism. The processors discussed earlier are all referred to as some type of scalar device. As name implies, vector processors deal with multiple pieces of data in the context of one instruction. This contrasts with scalar processors, which deal with one piece of data for every instruction.